Hi, the topic of this video is some basic set laws that concern operations on sets and allow us to review a little bit how do you prove things based on set equality and set inclusions, and also allows us to discuss a little bit of functions. So I want to prove a theorem with three parts here. A, B, and C are sets. And the first of these statements says that if I take the intersection of A with the union of B and C, I get the intersection of A with B and the intersection union with the intersection of A and C. Now, if one draws these statements of these are relatively intuitive graphically, if one say has B and C, one has a set A here, then the points that are in A intersect B union C consist of those points that are in either A or C, but also in A. So it would be this region in this picture. But this set can be thought of as a union of two parts, those that belong into C and A, and those that belong into B and A. So the statement is just a reflection of this graphical principle. So to show this, we have to, but in the rigorous proof, how do we show this? We show two parts, that A intersect B union C is a subset of A intersect B union A intersect C, and vice versa. So, because what this means is that every element here is also an element there, and the opposite in inclusion means that every element here is an element of there. That means that they share the same elements, and therefore they are the same set. Now, both of these proofs are fairly similar, so I will only do one of these directions. So suppose that X is in A intersect B union C, then X is in A and X is in B union C. So we know that X is in A, and we know that X is in B, or X is in C, one or the other. So there are now two cases that we have to consider. Case one, X is in B, and case two, X is in C. Whenever we have an or in our statement, or some cases that we depend on, we will have to divide into those cases. Now, in the X equal in B case, we still know that X is in A. So now we know X is in A and X is in B. So by definition, X is in A intersect B, because this consists of those points that are in both A and B, and we know that X in this case is both in A and B. But so X is also in A intersect B union A intersect C, because it's in the first set, and in the union it's sufficient that it's in one. So this is the end of the first case. Now we get the end of the proof. X equals C, similarly, we get that X is still in A, because that didn't depend on these cases, and X is in C. And so X is in A intersect C. Now, by definition of union, X is in A intersect C, union A intersect B, which is the same thing as A intersect B, union A intersect C. So either way, we get that every element of A intersect B union C is in the right-hand side. So these are the same thing. Indeed, if you think of just in English, this consists here of points that are in A and either in B or C. And this is the same thing as those points that are both in A or B, or both in A and C, because these are the only cases that you could belong on the left-hand side. So that is the proof of claim one of these directions. The other claim is very similar. You have to divide into two cases and go from there. Now, 2 here consider 2 and 3 concern complements, and these are called the so-called De Morgan laws. I won't prove both of them. I'll prove the first one because the second one is very similar and left as a good exercise. So if I take first the union of two sets and its complement, take first the intersection and then its complement, then this is the same thing as taking first the complement of A and then unioning with the complement of B. And again, graphically, as a using so-called Venn diagrams, we have some universe. The complement requires that we have some bigger thing that we're looking at. If we have the set A and the set B, well, the intersection would be those points that lie in both of them. So this little oval shaped thing in the middle. Now, if we take the points that don't belong there, we get all of these points that lie outside of this little oval in the middle. But we see what is another way of expressing this is that there are those points that lie outside of A, take union with those points that lie outside of B. And this is again sort of the proof analysis. So we will show that A intersect B complement is the union, it is contained in A complement union B complement. And this time I will also do the other direction, that A complement union B complement is contained in A intersect B. And these two together prove the claim. So we're showing A intersect B, a complement lies in there. So let's fix an X that lies in the complement. So X does not lie in A intersect B. So X does not lie in A intersect B. So what we know is not X in A and X in B. And from this, we know that this means that either not X in A or not X in B. This is equivalent. So either X not in A or X not in B. But this is the same thing as saying either X in A complement or X in B complement. And therefore, X in A complement union B complement. The other direction is very similar. Indeed, this could be written as just a sequence of equivalences. If X is in A complement union B complement, there are two cases. Case one, X is in A complement, so X is not in A. Therefore, so X is not in A intersect B, because that consists of points that are both in A and B, and if it's not in A, it cannot be in both. And therefore, X is in A intersect B complement. And the case two is X is in B complement, so X not in B, so X not in A intersect B, because again, it consists of those that are in both. And then we again get what we want is X in A intersect B complement. And we're done. Because this shows the two inclusions, the one hand this, and the other hand that. And we start from an arbitrary element, concluding that it lies on the right-hand side, an arbitrary element on the left-hand side, and conclude through cases that either lies on the left or the right. Now, the final thing I want to say about sets, it concerns functions on spaces. So if a function is some sort of identification between points in some domain of f, often called just x, and some set of possible values in y. And the crucial thing to be a function, it's really can be thought of as a relationship between the domain and the range, is that for every point in the domain, we have some point in the range, but not the other way around. So there might be some points in the range with no pre-image, no x such that f of x is equal to y. This is not, so the range might not be the full of y. And another crucial thing is that when we say that for every x we have a value y, that means that there for the same y we can have multiple x's, but for each of these x's we only have one arrow going to the right. So this is an example of a visual representation of a function from x to y. Now, based on that, we can define the image of a set and the pre-image of a set. And again, I define them in a way that emphasizes how you prove them. So the image, how you use them in proofs. F of A consists of all those elements such that there exists an x, such that we have fx equals y. And this is often how you use f of A. Now the pre-image of set B, it consists of all those x's such that f of x, the image point, is contained in B. And of course, all these x's are only in the domain of f. Now, using this notation, we can say that the range of f is equal to f of x, because this is equal to all those y's such that there exists some x in the domain of f, such that f of x is equal to y. So that's another expression for the range of f. It might not be all of y, as we know. Now, in analysis, often you have to take functions of unions, intersections, or pre-images, and these one has to be a little careful about. And the relationship, what happens for the function if we have a union of a set, so x lies in one of the AIs, this is the same thing as, say, if x lies in one of these domain sets, then the image point will also lie in one of the images And this gives the equality of images of unions as the union of images. However, intersections, because the function may not be one-to-one, behave slightly differently, and this equality becomes a subset relation, and this is sharp. You cannot improve this into an equality. But for the pre-images, things are nicer. In that case, it works both ways, that the union of pre-images is equal to the pre-image of the union, and the intersection of pre-images is equal to the pre-image of the intersection. Now, these can be again proven. I'll prove just quickly two to show you how these definitions of the intersections are used. If X lies in the image of the intersection, well, let's use Y here to emphasize that this is in the image side. Then, by definition of the image set, there exists an X that lies in the intersection, such that f of X is equal to Y. But then, for all I, X is in AI, and f of X is still equal to Y. But this means that for all I, Y is in the image of f of AI, and this is the same thing as saying that Y is in the intersection of f of AI. So that's how you prove that something is in an infinite intersection. Now, for the unions, I won't prove all these, but I will say something about case 3, about pre-images. This now consists of two inclusions, the pre-image of the union being contained in the union of the pre-images, and then the other direction, which I won't prove now. This is left as a thought exercise, or you can consult any simple book, say Rudin's Real Analysis probably will contain this in the beginning. So let's prove the first part. If now we are working in the range sign, so I use an X to indicate this. So if X is in pre-image of the union, then that means that f of X is in the union of AI. That means that there exists an I such that f of X, this I should be an I if we want to make this perfectly rigorous, fx is an AI, but fx, there existing an I such that fx is an AI, means that there exists an I such that x is in the pre-image of AI, and this is the same thing as saying that x is in the union of f inverse I. And actually, the other as a hint for the other direction is you can convert all of these into equivalences. You can do this argument the other way around, and that is what you should do here. So this was a review on basic proofs on sets.